Have you ever wondered what it would take for people to accuse NASA of straight-up lying? Not just hiding a detail, but delaying images, editing frames, shaping a story. That is exactly what's being claimed about the interstellar visitor, 3IATLAS, an object from outside our solar system, weird data, and a gap before the pictures appeared. For some, that gap is enough to say, NASA delayed the images to perfect their lie. Is that fair? Or just fear? Tonight on Sleep Astronomy, we're going to pick this apart slowly, if careful. Skeptical journeys are your thing. A quiet like and subscribe helps others find us. For now, settle in and let's see how much of this story survives contact with the facts. NASA has now released the high-resolution images of 3IATLAS that were held back for more than 40 days. The press conference, the carefully edited visuals, and the prepared statements have already shaped how most people think about this object. To understand what that release really means, it helps to step back and look at the pattern behind it, and to compare what was promised with what was actually done. Not long before the 3IATLAS campaign, during the Mars Biosignature press conference, NASA invested a great deal of effort in telling a particular story about itself. The agency presented an image of being transparent, open, and fully trustworthy. The language was deliberate. Phrases were repeated. The role of NASA was framed in a very specific way. Secretary Defy opened that earlier event by reminding the audience that, for more than 30 years, whenever NASA thought it had detected possible signs of life, it had shared those results with the scientific community immediately. The central claim was clear: fast release, peer review, radical openness. Nikki Fox then reinforced the point with stronger wording. She described how, the moment a signal was found, the images were put out for everyone to see and to share. These were not off-the-cuff remarks. They were part of a coordinated communication strategy designed to lock in an image of NASA as an institution that never sits on important data, never waits, and never filters. In that context, her description of NASA as ultra-transparent and her remark that withholding exciting news would rightly make people think the agency was hiding something were crucial. Those statements defined, in NASA's own words, what hiding would look like. By that standard, a long delay is not neutral. It carries meaning. Later in the same Mars event, Lindsay Hayes echoed the same structure. First, announce that a signal has been detected, then publish a paper that explains the context. This sequence was presented as the honest way to work. Announce, explain, call that transparency. At the same time, it also gave NASA a way to shape the story by pairing every announcement with an official interpretation. Every spokesperson followed the same pattern and nearly the same lines. We will be transparent. If we have exciting news, we will share it. We will continue to tell you what we find, what we see, and what we think. Now set that promised behavior beside what happened with 3IATLAS and the high-resolution images. The Mars Reconnaissance Orbiter took side-view images of the interstellar object on the 2nd and 3rd days of October, from a distance of roughly 29 million kilometers at a resolution of about 30 kilometers per pixel, several times better than what the Hubble Space Telescope could achieve for this target. Those frames did not appear publicly for more than 40 days. In that interval, the explanation given to the public centered on the government shutdown and on internal procedures. Meanwhile, 3IATLAS moved along its path. Time-sensitive data that could have helped shape a global observing campaign were not available. Images that might have guided telescope scheduling, helped teams coordinate, or resolved early questions about nucleus size and jet geometry, stayed inside institutional systems. During this pause, a different kind of activity began. Mainstream coverage started to prepare expectations ahead of the release. Articles highlighted radio detections of hydroxyl and framed them as evidence that 3IATLAS is a normal water-bearing comet. Stories about the best-ever images emphasized how exciting the views would be, while also reassuring readers that nothing in them would overturn standard comet science. The conclusion was offered early. Ordinary interstellar comet, unusual but natural. That is not just neutral reporting. It is a kind of narrative management. The pattern was clear. First, shape the public interpretation. Emphasize water. Emphasize that interstellar comets are expected to be diverse. Describe the object in familiar terms. Then, when the images arrive, they fit into an already prepared story. Most people, having absorbed the message that this is a comet like the others, will not question that frame, even if some details do not sit comfortably inside it. Set that careful rollout beside the behavior of 3IATLAS itself. Observations have shown a sunward anti-tail that is difficult to reconcile with standard dust-tail physics. Jets that appear to fire both toward and away from the sun. Unusual chemistry reported in more than one independent study, and a path closely aligned with the ecliptic plane with a quoted probability in the range of a few tenths of 1% for a random interstellar visitor. It is an object roughly the size of Manhattan, crossing the inner solar system with properties that do not match the training set of traditional comet expertise. Taken together, these features sit awkwardly with a simple, just another comet narrative. The actual NASA presentation, when it arrived, matched many of the expectations that could be inferred in advance. The high-resolution images were shown in a processed form, suitable for public viewing. They were scaled, smoothed, and annotated to make the nucleus easy to see and to fit within a coherent story. The conclusion offered was that 3IATLAS is a natural interstellar comet, emitting water and other volatiles in ways that, according to the speakers, can be understood within existing models once the data are fully considered. What did not appear, at least in the public briefing, was an immediate, broad release of raw FITS files for independent analysis. Attractive image products were shared quickly, as promised. The deeper data, with full calibration and unprocessed pixel values, began moving into archives on slower timelines, through channels that require more specialized access. There was limited direct engagement with the full list of reported anomalies. Individual points could be addressed in isolation, but there was no extended discussion of the compound improbability of all the features occurring together in one object. Some aspects of transparency were visible. NASA did, in the end, show the images. They described their methods and linked the high-resolution views with other measurements, including hydroxyl detections that point to water outgassing. They spoke about ongoing work and upcoming publications. At the same time, the flow of information was clearly controlled. Only certain questions were taken. The 40-plus day delay was framed as an outcome of policy and process, rather than as a choice, in tension with earlier promises of ultra-transparency. The Mars Biosignature press conference gave us NASA's standard in their own words. Put out images for everyone to see. Share what you find as soon as you find it, and avoid any appearance of hiding. The 3IATLAS rollout showed how that standard plays out when stakes are higher and public attention is intense. The result sits somewhere between full openness and carefully managed communication. This leads to a broader point about what transparency means in practice. True transparency is not the same thing as frequent updates. or polished visuals. An agency can speak often and still be opaque if key data remain inaccessible or if difficult questions are consistently sidestepped. Real openness would mean releasing raw data as quickly as practical, explaining delays in detail when they occur, being explicit about uncertainties, and resisting the urge to lock in one interpretation before the wider community has had a chance to examine the evidence. In the weeks when the high-resolution 3IATLAS data were held back, other groups did not wait. Amateur observers continued to track jets and ghost-like shells. China's Tianwen-1 probe released its lower-resolution images without long delays. Ground-based observers published spectra and images from modest equipment, showing structures and behaviors that did not always line up neatly with simple comet models. Scientific work continued, but without the best available images that could have helped resolve key questions. 3IATLAS itself did not slow down for internal reviews. Its jets changed. Its brightness evolved. Some features may have been transient, visible only for a short time. Every day without full access to the highest quality data was a day when some chance for coordinated observation was lost. The NASA presentation that finally arrived was, as expected, professional and impressive. The speakers were competent. The explanations were clearly delivered. The images were striking. None of that is a problem by itself. The important thing, especially for anyone trying to understand what 3IATLAS really is to remember that a polished event is not the same as complete transparency, and a confident narrative is not the same as a full accounting of all the evidence. The remaining work now sits with the broader community. Independent teams can request the raw data, compare it against their own observations, and test both normal comet models and more adventurous hypotheses. The contrast between rhetoric and reality during this episode, between the promise of instant openness and the reality of a long, publicly debated delay, will remain part of the larger story of how we respond when something genuinely unusual passes through our solar system. Seen in hindsight, the way 3IATLAS has been handled still does not line up with the simple idea of clean, fast, fully open science. The long delay, the careful staging, and the strong messaging are easier to understand as institutional control than as pure scientific necessity. To see why this object created so much tension between words and actions, it helps to look directly at the anomalies themselves. Astrophysicist Avi Loeb and collaborators have pulled together a list of 12 separate oddities linked to 3IATLAS. Each one can be debated, and some are now being re-examined in light of new data from NASA. But when you place them side by side, the overall picture is still striking. The first anomaly is the path of 3IATLAS. It follows a retrograde orbit that is aligned to within about 5 degrees of the ecliptic plane. Interstellar visitors should be able to arrive from almost any direction in three-dimensional space. Unless an object is tied to the disk that formed the planets, there is no special reason for it to line up with that disk. Estimates put the chance of a truly random interstellar object passing this close to the ecliptic at around 0.2%. Low, but not impossible, and it is the first reason people began to pause. The second anomaly is the so-called sunward anti-tail, seen in July, August, and again near early November. In normal comet physics, dust is pushed away from the sun by radiation pressure. Sunlight transfers momentum to grains and drives them outward. For material to move toward the sun, against that push, another force must act in the opposite direction with greater strength. Standard sublimation of ice does not provide that. The geometry does not cooperate, yet 3IATLAS shows a clear, repeated sunward feature that is hard to explain as a simple projection effect. The third anomaly links mass and speed. Current estimates suggest that 3IATLAS has a nucleus roughly 1 million times more massive than Oumuamua and about 1,000 times more massive than Comet Borisov, while also moving faster than both. In general, large objects wandering between stars are expected to be rare because gravity tends to capture or strongly deflect massive bodies over long times. Finding something both very massive and moving very fast lies in a probability range often quoted below 0.1% for the population we expect to detect. The fourth anomaly concerns timing and geometry. The orbit of 3IATLAS carried it within tens of millions of kilometers of Mars, Venus, and Jupiter, while at the same time it was unobservable from Earth around perihelion because it passed behind the Sun from our point of view. In a vast solar system, with planets occupying small regions in a lot of empty space, having an interstellar object graze several major planets and still manage to hide from Earth at the moment of closest approach demands very specific timing. One estimate puts this at about 1 in 20,000. Again, not impossible, but when such odds start to stack, they create discomfort. The fifth anomaly involves chemistry. Early measurements suggested that the gas plume around 3IATLAS contains significantly more nickel than iron. In standard stellar processes, iron and nickel are produced together in fairly stable ratios. Interstellar dust and primitive solar system material reflect those ratios. Seeing strong nickel without matching iron is odd. It resembles the kind of skewed ratio you might expect from nickel-rich alloys manufactured for particular uses. Reports also noted a nickel to cyanide ratio much larger than in other comets, including Borisov. Even as newer observations from NASA and other teams firm up the presence of water and other volatiles, this unusual heavy element pattern remains a point of discussion. The sixth anomaly is the reported low water content. Several early spectroscopic analyses found only a few % water by mass in the plume, far below what standard comet models would expect for an object that looks so active. In classical comet science, water is the main volatile. Heat up a dirty snowball, and water vapor is usually the dominant gas. A 4% water fraction looks more like a mostly dry body with a thin veneer of water-rich material. New detections of hydroxyl, a breakdown product of water, show that 3IATLAS does carry and release water, and NASA has used that result to support the normal comet view. The tension now lies between those newer measurements and the earlier indications of gas-poor spectra from ground-based observers. The seventh anomaly relates to polarization, the way light is oriented after scattering from dust. 3IATLAS shows extreme negative polarization that does not match what has been seen in other comets, including Borisov. Polarization depends on grain size, composition, and structure, and comet dust has been studied in detail for decades. The signal from this object looks like an outlier, hard to reproduce with known mixtures of natural materials in normal size distributions. The eighth anomaly is a loose directional link to the famous WOW signal, a strong radio burst detected in 1977 in the direction of Sagittarius. 3IATLAS approaches from a direction that matches that region to within about 9 degrees. 9 degrees is not tight aiming and could easily be coincidence. On its own, this overlap would not be worth much. As one more low likelihood detail in a growing list, some people include it in the overall probability stack, while others treat it as noise. The ninth anomaly arises near perihelion. 3IATLAS brightened faster than any known comet on record and became bluer than the Sunday. Normally, as a comet heats, it becomes redder because dust dominates the scattered light, and thermal emission shifts toward longer wavelengths. Blue color requires either very fine dust with unusual scattering properties or some separate mechanism that emits strongly at short wavelengths. For this object, both the rate of brightening and the color change are difficult to fit with standard sublimation curves. Here too, official models now argue that combined water and carbon-bearing gases can account for the behavior, while critics point out that the detailed light curve still departs from typical patterns. The 10th anomaly focuses on the jets and their energy source. The combined sunward and antisolar jets imply a high mass flow. If sunlight warming exposed ice is the only power source, you need a very large active surface area to absorb enough energy. When researchers calculate the incoming solar energy, the sublimation rates, and gas expansion needed to produce the observed jets, they struggle to fit everything within the current size estimates for the nucleus. Either the relevant surface is much larger than the nucleus appears to be, or some additional mechanism is contributing energy. The 11th anomaly looks at non-gravitational acceleration. Near perihelion, 3IATLAS's path showed shifts that, in standard models, would require shedding at least about 13% of its total mass. That level of mass loss in a short time is violent. In other comets, such events lead to obvious breakup or multiple fragments. Early imaging, and now even the higher resolution Mars data, suggest that the object remained mostly intact, without a clear debris cloud. There is a gap between the acceleration implied by the orbit fit and the visible signs of mass loss. The 12th anomaly concerns jet alignment over long distances. Observations show narrow, well-collimated jets that remain pointed in stable directions over hundreds of thousands to around 1 million kilometers, even though the nucleus is rotating. In normal comets, as the body spins, active patches sweep around and jet directions change, like beams from a rotating lighthouse. For 3IATLAS, the jets seem to keep fixed orientations while the object turns. That could only happen naturally if the rotation were extremely slow in a very specific way, or if there were some mechanism that actively adjusts the jets to compensate for rotation. Neither option fits easily with standard comet physics or with current rotation estimates. When you step back and consider all 12 together, you are no longer dealing with a single odd curve or one unusual spectrum. You are dealing with a pattern of outliers. Each anomaly by itself might be chalked up to rare conditions, measurement error, or gaps in our models. When you treat them as independent and multiply their quoted probabilities, you reach numbers so small that just a strange comet begins to sound like an increasingly fragile claim. This is where the usual tools of scientific reasoning start to press in uncomfortable directions. You can, in principle, build a natural explanation for each item on the list. You can assume a rare orbital history to explain the trajectory, a rare parent body for the chemistry, unusual surface structure for the jets, special radiation processing for the low water fraction, and so on. But as you stack these special cases, the combined scenario becomes more and more finely tuned. Occam's razor, the idea that we should favor simpler explanations that match the data, starts to point toward the possibility that these anomalies are not independent at all. A single underlying cause might generate several of them at once. Precise trajectory, alignment, unusual chemistry, stable jet orientation, preserved structure under odd acceleration, and carefully tuned geometry are exactly the kinds of features that make people start to ask whether design, rather than pure accident, could be involved. The questions that follow sound like science fiction. What if the close match to the ecliptic is not random, but targeting? What if the low water content reflects a deliberate material choice? What if the jets holding their direction against rotation reflect active control instead of passive outgassing? It is possible that there are entirely natural processes we do not yet understand that produce the same signatures. Perhaps there are rare environments around other stars that build objects with exactly these properties. But intellectual honesty requires that we admit the other option, that an artificial origin, a constructed object on a deliberate path, is not obviously less probable than the claim that 12 independent natural anomalies all happen to land in one object by chance. Loeb often points out a training data problem. Comet experts have spent their careers studying icy bodies from our own solar system, which formed about 4.5 billion years ago in our sun's protoplanetary disk. Their intuition and models are tuned to that population. When they see 3IATLAS, they naturally try to fit it into known categories. That is how expertise usually works. At the same time, humanity has already launched artifacts that will, given enough time, become interstellar. Probes, upper stages, even the Tesla Roadster will eventually drift between stars. If one of our objects passes through another system in the distant future, observers there will face the same question we face now. Will they recognize it as artificial, or will they treat it as a puzzling but natural rock? The point is not that 3IATLAS must be artificial. The point is that artificial should be allowed into the set of hypotheses we test, on equal footing with natural scenarios. If we refuse from the start to consider interstellar artifacts, we guarantee that we will never recognize one, even if it flies through our own sky. The 12 anomalies, even after new NASA data and official statements, do not amount to proof. They are not a final verdict. They are a set of observations that, taken together, indicate that something unusual is happening. The high-resolution images from Mars, now public in processed form and gradually becoming available in raw formats through archives, may resolve some of these issues. They may show surface structures that clarify jet geometry, fine fractures that help with the mass budget, or subtle signs of fragmentation that lower-resolution images could not reveal. Or they may add new puzzles of their own. Either way, the stack of anomalies is still there. It is that stack, not any single headline, not any single press conference, that needs to be explained. Seen from where we are now, with the Mars images public and NASA officially calling 3IATLAS a natural interstellar comet, the long delay still does not make much sense in terms of clean science or true transparency. It fits better as an example of institutional management. While large observatories debated definitions and agencies controlled when and how to speak, amateur observers were recording features that, under current models, ought not to exist at all. They reported nearly perfect circular shells expanding around the nucleus of 3IATLAS, detached rings, hanging in space like smoke rings that do not fade, but grow. These shapes run against everything we usually say about how gas and dust spread out from a comet into vacuum. The first reported ring appeared in routine monitoring images. It was faint, barely visible, a thin circle around 3IATLAS at a distance that looked strangely orderly. On the 9th day of November, the ring spanned about 1.2 arc minutes. 4 days later, on the 13th, it measured about 1.4 arc minutes. That is roughly a 20% increase in apparent size in only 4 days. The surprise is not just the expansion, it is the shape. The ring stayed circular, not slightly lopsided, but extremely close to a true circle as it grew. Under normal conditions, when a rotating, irregular nucleus releases gas and dust, the material spreads out unevenly. Some jets are stronger, some weaker. Different regions on the surface are more active than others. As the nucleus turns, these active spots move, sweeping material into spirals, arcs, and off-center clouds. The result is a structured coma, not a precise ring. In other words, we do not expect a clean, circular shell that maintains its form while expanding at a steady rate. Yet multiple observers documented exactly that. In amateur communities, this feature became known as the ghost shell. It behaved like an expanding bubble created by a single point source. But 3IATLAS is not a point. It is thought to be kilometers across, with a complex surface, multiple active areas, and jets in several directions, all on a rotating body. Simple, unstructured outflow does not naturally produce a stable, symmetric ring. Then another step was added. Observers found not just one shell, but a system of detached shells, 5 separate rings centered on the nucleus, but not touching one another, spread across a region about 150,000 kilometers wide, roughly 40% of the distance from Earth to the Moon. These were not thick, continuous shells like the layers of an onion, but distinct, ring-like structures with clear gaps between them. Each ring held its shape as it moved outward. The system covered a volume of space larger than many interplanetary orbits and still looked organized. There was spacing, there was regularity. When comets release material, it usually forms a coma that resembles a cloud with density falling off gradually. It does not normally organize itself into separate, well-defined rings with measurable separations. The images that showed these shells did not come from billion-dollar missions. They came from backyards and small observatories, from people using commercial tracking mounts, modest telescopes, and cooled cameras. Anyone with enough interest can buy. Yet they were seeing structure that large survey projects did not report, or at least did not highlight in public discussions. Even after NASA's Mars images and press materials focused on the nucleus, the jets, and the conformation of water through hydroxyl detections, these ring structures remained mostly an amateur topic. One reason may be the way professional systems are tuned. Large surveys are often designed to find point sources like asteroids or broad diffuse objects like galaxies and nebulae. Their software and analysis pipelines are optimized for those tasks. Unusual shapes can be flagged as noise, background variation, or instrumental effects, and automatically downweighted or ignored. A faint ring around a bright point may simply not survive those filters. However, when multiple independent observers using different telescopes, different cameras, and different optical setups all record similar rings, the simple artifact explanation begins to fail. Instrument problems usually follow one specific system. Processing mistakes usually appear in one person's workflow. They do not repeat across unrelated hardware and independent reduction methods. When the same structure appears in raw frames taken by different people, the simpler conclusion is that the structure is real. That leaves the difficult part, explaining what it is. Several ideas have been proposed to account for the shells. The first and most conservative suggestion is that 3IATLAS experienced discrete outbursts. In this picture, each shell comes from a separate event, a sudden release of material that expands outward, roughly as a sphere. If there were 5 major outbursts, each one could, in principle, generate one of the rings. The shells would expand at slightly different speeds, staying separated as they grew. On paper, that idea works, but it depends on very specific conditions. The outburst must be nearly isotropic, sending material in all directions equally. That is not how known comet jets behave. Jets tend to be narrow and directional. To approach a spherical pattern, the nucleus would need to rotate quickly during the event, so that jets sweep over many directions. Averaging out, yet earlier observations of 3IATLAS suggest a relatively slow rotation, not an extremely fast one, and reports of jets keeping stable orientations do not sit comfortably with rapid spin. The isotropic ejection model solves one problem and creates others. A second idea looks to the solar wind. Perhaps material from 3IATLAS is being shaped by the stream of charged particles flowing out from the sun and by the solar magnetic field. In this scenario, plasma effects and magnetohydrodynamic forces would carve the material into ring-like forms as it expands. The solar wind does carry magnetic fields and can influence the motion of charged dust and ions, but the forces involved are weak. They can gradually push on particles over long distances and long times, yet organizing them into crisp, concentric shells is another matter. To form and preserve ring structures, the shaping forces must overcome the initial spread in velocities from the ejection event. The rings would also have to survive differences in solar wind pressure at different distances from the sun and across different parts of the structure, as well as variations from the spiral pattern of the interplanetary magnetic field and from changes in solar activity. It is not impossible, but it requires a very delicate and stable balance. A third hypothesis steps further into speculation. Instead of shells of material simply expanding, what if we are seeing standing wave patterns? In that case, dust and gas might concentrate at nodes in a wave field, where oscillations in density occur. Creating standing waves usually calls for boundaries or cavities that reflect waves back and forth. That is hard to arrange in open space. Some have argued that if 3IATLAS had a strong magnetosphere, an area dominated by its own magnetic field, and if ionized material in the coma interacted with that field, complex wave patterns could arise, organizing material into ring-like zones. But standard models do not give comets strong intrinsic magnetic fields. They are not thought to have metallic, rotating cores like planets. To grant 3IATLAS such a field would require new mechanisms beyond current comet theory. It is important to note that the amateurs who reported these shells are not inexperienced observers chasing dramatic claims. Many have spent decades imaging comets, asteroids, and deep sky objects. They understand calibration, flat fields, dark frames, and how to correct for sensor noise and optical ghosts. When such observers insist that a structure survives careful checking, their work deserves serious attention. One detailed study combined images from several nights into a time-lapse sequence. Frame by frame, the ghost shell grew. The ring moved outward while preserving its circular shape. From the change in apparent size, the expansion speed was estimated at about 500 meters per second, a value that fits within the range expected for dust and gas leaving a low-gravity body. The speed itself is not surprising. What remains unexplained is how an expanding shell of particles maintains such smooth symmetry over tens of thousands of kilometers. Another observer noticed gentle brightness variations along the ring. These were not random clumps. They appeared to follow subtle patterns, repeating at specific angles. It was as if the ring had preferred directions, possibly aligned with something external, such as the direction of the solar wind or the orientation of the ecliptic plane. The data were not strong enough to fix a definite alignment, but they hinted that the rings might be oriented in a meaningful way. rather than being fully uniform. There is also a question of mass. To create 5 visible shells spanning thousands of kilometers, 3IATLAS must release a substantial amount of dust. If all of that comes from the nucleus, then significant erosion is taking place. That raises further questions. Is the nucleus losing layers in a simple, one-way process, like a surface being sandblasted? Or is some material being trapped and reused, moving in cycles that we do not yet understand? Professional astronomers did notice these reports. Some reached out to the amateur community asking for raw data, calibration files, and details about the imaging setups. There were first steps toward collaboration. Yet in NASA's official messaging and in most mainstream summaries, the shell structures have had little or no presence. The focus has stayed on the bright core, the jets, and now the confirmed water and other volatiles that support the natural comet interpretation. The rings do not fit easily within that simple story, so they remain at the margins. This pattern is not unique. In astronomy, discoveries from non-professional observers often take time to be checked and integrated. Skepticism and careful verification are part of healthy science. But for a fast-moving object in the inner solar system, time is limited. 3IATLAS is changing as it travels. By the time a feature is officially validated, it may have faded. The ghost shell mystery highlights a broader issue about how we study transient events. 3IATLAS is not a fixed sample in a lab. It is moving through a changing environment, responding to sunlight, solar wind, and its own internal structure. Features visible near perihelion may disappear as it moves outward. Delays in taking such reports seriously can mean losing the chance to study them forever. There is a real possibility that the shells are present, at least faintly, in the data from Mars. Whether they show up in the currently released processed images or only in raw frames and deeper analysis is not yet clear from public material. Spacecraft cameras have limited dynamic range. If you expose for the bright nucleus, the faint outer structures can vanish. If you tune for the faint halos, the core may saturate. It is not always possible to capture both cleanly. What the amateur data make clear is that 3IATLAS is more complex than a simple dirty snowball. The closer people look, the more structure appears, and when that structure includes neat circles, concentric rings, and organized patterns that are hard to generate from basic outgassing and dust dispersion, we are pushed toward harder questions. One possibility is that we are seeing natural physics we do not yet fully grasp, processes that occur in material that has spent immense time in deep space, exposed to cosmic rays and interstellar conditions unlike anything near the Sunday. When such material is heated after billions of years, it may behave in ways our current models do not predict. Another possibility is more unsettling, that some of the order we see is not accidental. Rings that hold their form might do so because they were meant to. Geometry that looks designed might be designed. This does not mean we know that 3IATLAS is artificial. It does mean that this option should not be excluded simply because it makes us uncomfortable. For now, the shells continue to expand. They can still be observed with well-prepared equipment and clear skies. They do not vanish when ignored. They remain as visible, measurable structures around 3IATLAS, waiting to be studied carefully, explained honestly, and included in any serious attempt to understand what this interstellar visitor really is. Spectroscopy adds another piece to this puzzle, and even after NASA's latest statements, it remains hard to ignore. Before the big facilities finished their careful analyses, and before the Mars images were released, a civilian observer with modest equipment managed to capture a surprisingly clean spectrum of 3IATLAS. They used an 80mm refractor, a Star Analyzer 100 grating, and a cooled monochrome camera. The data were handled seriously. The spectrum was extracted with custom Python code, cleaned for contamination, and calibrated against standard stars. The wavelength range covered roughly 628 to 880 nanometers, from the deep red edge of visible light into the near infrared. When the analysis was finished, around 30 spectral peaks were identified and catalogued, all of them traced back to dust. None of them showed clear signatures of gas in that window. That was the impossible part at the time. 3IATLAS shows a bright green coma in images from many observers. It shows strong, structured jets, reaching tens of thousands of kilometers from the nucleus. By eye, everything about its appearance says active comet, releasing gas that drags dust outward. In standard comet physics, that kind of activity should leave obvious fingerprints in the spectrum. Lines from cyanogen, diatomic carbon, ionized carbon monoxide, water, and other common molecules. In this particular dataset, those lines were missing. No CN, no C2, no CO+, no water bands in that red to near infrared window. The green color made the result even more puzzling. In every well-studied comet so far, a green glow in the coma comes from diatomic carbon molecules. These C2 molecules absorb solar ultraviolet light and then re-emit it, producing the swan bands in the green part of the spectrum. Over time, this has become almost a rule of thumb. Bright green coma implies C2 emission. With 3IATLAS, the coma was clearly green, but the expected C2 features were not seen in this amateur spectrum. Several simple explanations were tested. One idea was that the equipment was not sensitive enough. An 80mm aperture and a modest transmission grating are not the same as a large research spectrograph. Perhaps the emission lines were just too faint, but the spectrum itself was not dominated by noise. The peaks were sharp, the continuum was smooth, and the signal-to-noise ratio was good. If strong C2 emission were present, it should have risen well above the detection threshold. Another thought was that the observations simply missed the key wavelengths. The main C2 bands lie near 516 nanometers, bluer than the range observed here. That is true, and this spectrum does not cover the classic swan bands. But other gas species have features in the red and near infrared. Water has bands there. Cyanogen has lines there. Several typical comet gases leave at least some signature between 628 and 880 nanometers. In this particular set of data, none were clearly seen. A third possibility was timing. Perhaps the comet was in a quiet phase. Maybe jets had paused and gas production had dropped below detection limits. If that were the case, you might expect the comet's visual appearance to be subdued at the same time. Instead, imaging taken around the same dates showed a bright coma and obvious jets. In other words, the object looked active, while the spectrum in that window said, dust only. What the spectrum did show clearly was a continuum. Smooth light from solid particles warmed by the sunday. The 30 peaks were essentially points along a red sloping curve. That slope is consistent with old, space-weathered dust. Temperature estimates from the continuum matched what one would expect for dust grains at that distance from the sun in thermal equilibrium. On this point, the civilian data lined up with results from professional facilities. Larger telescopes, observing in similar bands, also reported a red continuum with weak or absent volatile signatures before and after perihelion. NASA's more recent work added an important piece: detections of hydroxyl, a breakdown product of water, showing that 3IATLAS is releasing water vapor, at least at some stages and in some regions. That result supports calling the object an interstellar comet rather than something entirely dry. But it does not remove the tension. We still have red, dust-dominated spectra in some wavelength ranges where normal comets show gas, sitting alongside images of a bright green coma and powerful jets. So we are left with a contradiction: a red, dusty spectrum with few or no gas lines matches an object that is quiet, inert, and largely depleted of volatiles, or one whose gases emit mainly outside the observed window. The images match an object that is bright, green, and throwing out material in large plumes. Natural comets are not supposed to look like one thing and spectroscopically behave like the other. Yet the current dataset forces us to hold both pictures at once. There are two broad ways to interpret this tension. One is that the green color is not coming from the usual diatomic carbon emission at all, which would force some adjustment to a basic piece of comet science. Another is that gas emission is occurring, but in forms, regimes, or wavelengths our current ground-based observations did not catch, either shifted into the ultraviolet and far infrared, where space telescopes are needed, or tied to more exotic chemistry or plasma processes. There is another layer that makes many astronomers uneasy: a smooth, largely featureless continuum, with no strong emission or absorption lines, is also characteristic of reflected sunlight from solid surfaces, rock, metal, or processed minerals coated in fine dust. If the surface is relatively uniform, the reflected light simply follows the sun's spectrum, reddened by dust and space weathering. In that case, spectroscopy tells you that you are seeing warmed dust or a dust-covered surface. It does not tell you whether that surface belongs to an untouched natural body or to an engineered structure buried under insulation. In other words, a red continuum by itself cannot distinguish between a very old natural object and a metallic artifact that has gathered dust. Both scenarios can produce similar spectra. That does not prove any artificial origin for 3IATLAS. It simply means that spectroscopy alone cannot rule it out. The data confirm that dust dominates and that familiar gas signatures are weak or missing in that particular band. Beyond that, they say little. The behavior of the jets adds more tension. Around the 15th of November, 3IATLAS appeared relatively calm in some reports, a green coma, but no strong jets. By the 16th, jets had returned at full strength in large, symmetric plumes, extending both toward and away from the Sunday. In standard comet behavior, jet strength follows solar heating and rotation. As the nucleus spins, different active regions face the Sunday. Jets brighten and fade over hours. They generally do not disappear for a full day and then return at the same level, unless the rotation period is extremely long, or unless something beyond simple solar heating is controlling their activity. Current rotation estimates do not favor an extremely slow spin. Taken together, a dust-dominated spectrum in that wavelength range and intermittent strong jets hint at a driving mechanism that is at least more complex than basic water-ice sublimation. If simple ice turning to gas is not the only engine, what else might be involved? One concept is dust jets driven with minimal gas. In principle, electrostatic forces could lift fine particles off a surface and push them outward, or mechanical processes like cracking and landslides could loft dust into space. But dust-only jets tend to be more diffuse and slower to accelerate. They do not usually form the tight, well-shaped plumes seen in many images of 3IATLAS, and even dust lifting from a surface that once had ice should release at least some vapor. Another idea invokes plasma. If 3IATLAS builds up electrical charge as it moves through the solar wind and then discharges, those events could accelerate dust and ions into narrow beams. The green glow might come from excited plasma, where ionized particles emit light at particular wavelengths. Some plasma conditions do produce greenish emission. However, small natural bodies are not generally thought to accumulate the sort of charge or maintain the kind of current systems needed for large, organized plasma jets. That would require specific electrical environments and internal structure that standard comet models do not include. It is also important to remember that this civilian spectrum covers only one window. If 3IATLAS is releasing unusual molecules, or if its main volatile activity occurs in the ultraviolet or far infrared, then a 628 to 880 nanometer slice can easily miss key lines. Space-based ultraviolet observations and longer wavelength infrared work are better suited to some of these questions. Professional facilities using broader coverage have already started to refine the picture, confirming water via hydroxyl and searching for other gases. Access to those instruments is limited, though. Proposals must be submitted, reviewed, and accepted, then scheduled into crowded observing queues. Meanwhile, 3IATLAS is moving away from the ideal geometry for many kinds of measurements. The best window for detailed spectroscopy is closing. If some observations are not made in time, the object will fade and opportunities for clarity will be lost. This is where the civilian spectrum shows its value. While official processes moved through their cycles, an individual observer pointed a small telescope at a unique object and collected data. The result is not a complete professional data set, but it is real information stamped with a specific moment in the object's evolution, and it does not line up neatly with expectations. Citizen science fills gaps of this kind. It does not replace large observatories, but it adds coverage when official channels cannot move fast enough. Dedicated observers with modest equipment can catch events that formal programs overlook or that they have not yet decided to prioritize. Sometimes those efforts produce artifacts. Sometimes they reveal new behavior. The spectral result ties directly into the question of what 3IATLAS is made of. If it were a water-rich comet, like those in our own solar system, we would expect strong water features across multiple bands. If it was strongly carbon-rich, we would expect the familiar carbon-based emission bands that explain green coma elsewhere. If it were a primordial dust clump from a very old system, we might hope for signatures that hint at that origin. Instead, in this observed range, we see only dust. One natural picture is that 3IATLAS is a very old, heavily processed object. Perhaps it formed in the outer parts of another star system, or in interstellar space itself, then traveled for billions of years under constant exposure to cosmic rays and background radiation. Volatiles could be stripped away, leaving a hardened, red, dusty body with limited gas left to release. That would match the red continuum and help explain weak gas signatures in some bands. It still has to be reconciled with a bright green coma, strong jets, shells, and jets that appear to hold their direction in spite of rotation. Another, more speculative, picture starts from the idea of long-term survival in deep space. If someone wanted to send an artifact between stars and have it arrive in working condition, they would likely build it to withstand radiation, dust impacts, and temperature extremes. They might wrap it in sacrificial layers of dust and rock, designed to absorb damage After such a journey, its spectrum could look like a dust-covered rock, very similar to an inert natural body. And if it had systems that activated near a star using stored volatiles, electric power, or other mechanisms, its jets might not follow the simple patterns we expect from ice sublimation. Activity could switch on and off according to internal cycles rather than sunlight alone. These ideas are speculative, not conclusions. They show how many different scenarios could produce a dust-dominated spectrum. Because of that ambiguity, we cannot simply point to spectroscopy and say, obviously natural, and we certainly cannot say, clearly artificial, on spectral grounds alone. The only firm statement we can make from this piece of evidence is that 3IATLAS does not fit neatly into standard patterns. In this band, its spectroscopic behavior does not match what our models would predict from its visible behavior. The researcher who took these data did not hide the methods. The spectrum, raw frames, calibration steps, and processing scripts were shared openly for others to check or repeat. Anyone with similar equipment can attempt to reproduce the work. That openness stands in contrast to the slow, managed release of some official data products. In this one narrow but important window, an individual with a small telescope has, in some ways, shown more immediate transparency than institutions with far greater resources. The high-resolution images from Mars cannot, by themselves, answer the spectral questions. Those cameras are built for detailed pictures, not for spreading light into spectra. But if they reveal particular kinds of surface patterns, color variations, or reflectance differences, they may still help. Combined with spectra across multiple bands, they could point towards specific materials or structures, or they may reveal new details that only deepen the puzzle. For now, the spectral result remains what it is: a bright green coma with no clear gas lines in this range, strong jets with no obvious volatile signatures there, and vigorous activity without the standard spectroscopic trace we would expect from the processes that are supposed to power it. 30 identifiable peaks saying dust, and an empty background where familiar gas lines would normally appear. Jets, at least in this part of the spectrum, that still do not follow the rules we thought they would. The jets from 3IATLAS still push hard against simple thermodynamics, even after NASA's new images and models. These are not tiny mismatches you can hide inside error bars. They touch basic questions about energy, momentum, and how gas behaves in near vacuum. Start with the energy budget. When ice turns directly into gas, it needs energy. For a comet, that energy comes from sunlight heating its surface. At any given distance from the sun, you can work out how much solar power hits 1 square meter, adjust for how reflective the surface is, and then estimate how much ice can sublimate each second. This is basic thermodynamics, the kind taught early in university. For 3IATLAS at perihelion, the solar flux was strong, and NASA's recent reports now point to water, carbon monoxide, and carbon dioxide in the outflow. If the surface has enough exposed ice, that radiation can drive a certain gas production rate. The problem is that the jets seen from Earth and from Mars still seem to imply a mass flow close to or above what that simple energy allows. Even if you assume very high efficiency, where most of the incoming energy goes into turning ice into gas, the active area needed is close to the full estimated surface of the nucleus. The margin is narrow. Small changes in assumptions push the system past what a compact, natural body can comfortably provide. On top of that, Jets are not gentle spherical flows. They are narrow beams. That kind of focusing needs conditions that guide the flow into preferred directions. In ordinary comets, you get some collimation from vents, cracks, and cliffs that act like crude nozzles, but these are usually small compared to the coma. The jets from 3IATLAS stay tight over thousands of kilometers, even in the new high-resolution Mars images, where NASA shows small pits and possible vents. The plumes we infer from ground-based data stay more focused over long distances than simple gas expansion would suggest. Direction adds another layer. Photometry and shape modeling now suggest that 3IATLAS rotates. Its brightness varies with a repeating pattern that NASA and other teams use to estimate a spin period. In a rotating body with fixed vents, jets should move across the sky as the nucleus turns, yet the main features, including the sunward structure seen in some images and the long tail pointing away from the sun, kept almost fixed directions for long stretches of time. For a spinning object, that leaves two broad options. Either the rotation axis happens to line up closely with the main jet directions, or the source regions somehow adjust to cancel out rotation. The first option is geometrically possible but not very likely by chance, especially when you consider several jets at different angles. The second option suggests some kind of regulation. Natural outgassing does not steer itself. It simply flows from whatever patch is lit and volatile. To maintain a nearly constant jet direction while the nucleus rotates would require something like nozzle steering in a rocket or a very special alignment of vents and spin. The timing behavior of the jets is strange as well. Before and around perihelion, observers reported periods when strong jets were clearly visible one night, then weak or absent the next, then back at full strength a day later. Over 24 hours, the distance from the sun barely changes. In the standard picture, active areas rotate in and out of sunlight. Individual jets brighten and fade, but total activity stays relatively steady because multiple areas contribute at different longitudes. You do not usually see almost all visible jets shut down and then return together on such short timescales. You can try to explain this by putting most active vents on one hemisphere that spends an entire rotation in shadow, then in light, matching an on-off pattern. That demands a very specific spin period and a very uneven distribution of volatile patches. Some models now go in this direction, but they require fine-tuning. Most well-studied comets do not show such extreme concentration of activity. They have several active zones that overlap and smooth the signal. The sunward jets, or sunward-looking features, remain a special problem. Ordinary dust and gas leaving a comet get pushed away from the sun by radiation pressure. To send material toward the sun, you need momentum in that direction. Something must push harder inward than radiation pressure pushes outward. In a few comets, so-called anti-tails can look sunward because of projection effects. The tail lies in the orbital plane, and our viewpoint makes it appear to point the wrong way. For 3IATLAS, geometry from different observing sites has been used to argue that at least part of the sunward structure is real motion, not just a trick of perspective. Electric fields could, in theory, pull charged particles toward the sunday. If 3IATLAS carried a large net charge and the solar electric field acted on it, ions could be directed inward. But to overcome radiation pressure on dust grains, the electric forces would have to be very strong. That implies high voltages and charge separation that small natural bodies are not expected to maintain for long. So far, there is no clear evidence of such extreme charging in the new data. Gravitational ideas do not help much either. A very massive body could, in principle, cause particles released on the far side to curve around and appear on the sunward side. But 3IATLAS is small. Its escape speed is measured in meters per second, while typical gas speeds from sublimation are in the hundreds of meters per second. Material is unlikely to fall back and orbit for long. It will mostly fly away. The mass loss implied by the non-gravitational acceleration introduces yet another difficulty. Early estimates suggested that, to match the observed changes in its path, 3IATLAS would need to lose a large fraction of its mass near perihelion. Later modeling, including work cited in NASA briefings, has tried to reduce that number by using more directional jets and more realistic shapes. Even so, the total mass loss required is not small. Comets that shed that much material in a short time often fracture. They split, leave bright debris streams, or break apart completely. So far, 3IATLAS appears to have stayed in one piece. Mars images show a compact nucleus. We do not see obvious large fragments, and there is no clear, broad debris cloud trailing behind at the level that early simple estimates might suggest. One way to soften this tension is to argue that pointed jets give more thrust per unit mass, like a rocket with a narrow exhaust. Directional outflow can improve efficiency. The latest models lean heavily on this idea, but even with that advantage, the curve is tight. Either we are missing part of the dust and gas budget, or some of the acceleration is coming from effects we have not fully included. Taken together, these points energy budget, strong focusing of jets, nearly fixed directions despite rotation, rapid on-off cycles, sunward-directed material, and the mass loss estimates do not slide neatly into the old picture of an icy body warmed only by the Sunday. Once or twice, you can call something an extreme case when all of them show up in one object. Natural explanations start to feel layered and complex. You can try shifting the basic assumption. Suppose 3IATLAS is not mostly water ice. Suppose it is mainly dense material with only small reservoirs of volatiles that fire intermittently. That can match low water fractions in some spectra and patchy jet behavior, but dry material alone does not easily explain a bright coma and large jets, and it does not fully fix the energy and direction questions. Alternatively, you can look for non-sublimation mechanisms. Perhaps dust is being lifted by electrostatic forces, by mechanical failure of the surface, or by reactions in complex organic compounds. We do see electric effects in dust devils on Mars, and impacts can throw material off a surface. Stored chemical energy can drive explosive releases. Some of these processes are natural, but none are known to generate the kind of long-lived, well-shaped jets seen in 3IATLAS without leaving clearer signatures we can recognize. Again and again, the conversation comes back to control. Not necessarily conscious control, but some kind of system that regulates output instead of just reacting passively to sunlight. Humans build engines with thrusters that turn on and off, change direction, and follow set schedules. At times, the behavior of the jets from 3IATLAS looks closer to that kind of regulated output than to a simple boiling surface. It is still possible to imagine natural settings that mimic control. You could picture an unusual internal structure where layers, fractures, and buried pockets of gas line up just right, so that heating triggers valves in a repeatable way. You could imagine slow internal changes that release gas in staged bursts. But to explain all observed features this way means stacking several rare conditions together. At some point, we have to ask a hard question. How many unlikely natural steps are we willing to multiply before we admit that our models might be incomplete? This does not mean jumping straight to exotic answers. It means leaving all reasonable hypotheses, including uncomfortable ones, open for testing. Now that the high-resolution Mars images are on the table, some parts of this picture are clearer. We see a small nucleus with surface texture, possible pits, and hints of vent-like structures. That supports at least part of the standard comet picture. At the same time, other parts are still cloudy. The images do not fully explain the long-range collimation, the jet timing, or the detailed non-gravitational acceleration. In some ways, the new data narrow the space for explanations. In other ways, they highlight what is still missing. Whatever 3IATLAS turns out to be, its jets are following their own rules. The physics at work is consistent in itself. The object responds to the sun in a repeatable way. The real gap lies in our understanding. Right now, our simple descriptions of how small bodies behave near a star do not fully account for what this interstellar visitor is displaying. Our assumptions about what natural objects can do after long journeys through interstellar space may need to be revisited, and over time, they may need to be revised at a basic level. While 3IATLAS pushes us to rethink how we view single objects moving between stars, another result is changing how we think about the stars themselves and the families they form. The Pleiades, the seven sisters, you can see with the naked eye on a clear night, are not just 7 stars, or even the few hundred that small telescopes reveal. They are now understood as the bright core of a much larger structure, more than 3,000 stars spread across roughly 2,000 light-years of space, about 20 times larger than older pictures suggested. This matters for 3IATLAS because it shows how easily we can misunderstand even very familiar things when our tools and methods are limited. The Pleiades have been part of human sky watching for as long as people have looked up. Ancient texts describe them. Many indigenous cultures use them in stories and calendars. Greek myth called them the Seven Sisters. Japanese tradition placed them in the Subaru symbol. These are not obscure, faint galaxies. They are bright, obvious stars. Yet we were off by about a factor of 20 in judging the real scale of their family. The new picture came from combining several kinds of data. NASA's Transiting Exoplanet Survey satellite, built to look for planets crossing in front of their stars, was also used to measure how fast stars in and around the Pleiades rotate. Rotation rate works like a cosmic clock. Young stars spin quickly and slowly lose angular momentum as they age. By measuring spin, you can estimate age. When thousands of stars spread over a huge volume all show nearly the same age, that is a strong sign that they were born together. The European Space Agency's Gaia mission added a second key piece. Gaia measures star positions and motions with very high precision. It tells us not only where stars are now, but how they are moving through the Milky Way. With that information, you can mathematically rewind their motion, tracing each star's path backward in time to see if their orbits converge. For the extended Pleiades group, those paths come together about 100 million years ago, when all of these stars occupied one broad star-forming region. Chemical data from surveys such as the Sloan Digital Sky Survey supplied a third test. Stars born from the same original cloud of gas tend to share a similar mix of elements. Different parts of the galaxy have been enriched by different generations of supernova explosions and stellar winds, so they have slightly different chemical flavors. Detailed spectroscopy gives each star a kind of fingerprint. The widely spread Pleiades members share matching fingerprints across the whole 2,000 light-year structure, confirming that they are, in effect, siblings. Rotation-based ages, motion traced backward, and chemical tagging together form a strong method for recognizing stellar families that are no longer tight clusters. Most groups of newborn stars do not stay bound forever. Over hundreds of millions of years, gravitational nudges from the rest of the galaxy slowly pull them apart. What once was a single cluster spreads out until its members look like random field stars. The newer techniques show that many of those isolated stars are actually related, still carrying signs of common origin even though they now lie far apart. This has broad implications. If the Pleiades are about 20 times larger than traditional views suggested, how many other clusters are also just the visible cause of much more extended associations? How much of the stellar population near the Sun belongs to large families we have not fully mapped yet? How much of what we call the local field might, in fact, be the dispersed remains of ancient clusters? There is also a direct connection to 3IATLAS. When we ask where this object came from, it is not enough to name a type of star or a rough patch of the galaxy. The environment matters. Was it born in a loose association, like the extended Pleiades, where close stellar encounters can disturb planetary systems and throw out comets and asteroids? Did it come from a dense cluster, a binary system, or a calmer, more isolated region? The conditions in its birth environment would shape its early history, its composition, and the chance that it was ejected into interstellar space. Even with NASA's recent Mars images and new ground-based data, that deeper origin story remains open. The age difference is striking. The Pleiades are young on galactic timescales, around 100 to 150 million years old. Their most massive members are hot, bright blue stars that burn fuel quickly and will explode as supernovae relatively soon, in a few 100 million years. Star clusters like this live and die over hundreds of millions to at most a few billions of years, depending on their mass and surroundings. 3IATLAS, by contrast, appears to be ancient. Surface radiation damage indicators and orbital modeling suggest it has traveled for billions of years in interstellar space. When it began its journey, the Pleiades as we see them now did not exist in their current form. The Sun was younger. Many of the stars we see in our night sky today were in different places or had not yet formed. 3IATLAS is likely a relic from an older chapter of the galaxy, carrying information about conditions that we can no longer observe directly. The discovery of extended structures like the Greater Pleiades also raises questions about our own star. Most stars are thought to form in groups, not alone. If that is true, the Sun probably has siblings, stars born from the same cloud about 4.5 billion years ago. Using the same approach applied to the Pleiades' rotation measurements, where they still help Gaia motions and chemical fingerprints, researchers have started searching for those siblings. For very old stars, that search is harder. Over billions of years, rotation rates converge, so spin is less useful as a precise clock. The longer we trace orbits back in time, the more small gravitational tugs from the galaxy blur the paths, making reconstruction of ancient positions less certain. Chemical tagging remains one of the best tools, but it needs very high precision to tell apart stars that are only similar from stars that are truly siblings of the Sunday. If we do manage to identify genuine solar siblings and study any planets and debris around them, the payoff would be large. We could see whether other systems born from the same material ended up with similar planet layouts, asteroid belts, or dynamical histories. That would help us understand whether our solar system is typical or unusual, and, by extension, how common certain kinds of planetary systems might be elsewhere. That kind of knowledge feeds back into our thinking about interstellar visitors, like 3IATLAS. What kinds of systems are likely to launch them, and under what circumstances? The Pleiades story also shows how much can be gained from using existing instruments in new ways. TESS was built to look for exoplanet transits, Gaia for precise positions and motions, and large spectroscopic surveys for mapping galactic chemistry. None of these missions were originally proposed with the specific goal of finding a 2,000 light-year-wide stellar family. Only when their datasets were combined with a fresh question in mind did the pattern emerge. This suggests that other hidden structures may be waiting in archival data. Telescopes on the ground and in space have been recording images and spectra for decades. Much of that information was collected for specific projects, then stored. A person with a new idea can return to those archives and search for signals that earlier teams did not think to look for. In principle, 3IATLAS itself could benefit from such work. Past sky surveys might have caught it faintly, long before anyone knew it was interstellar. Old photographic plates or digital surveys might show it as a barely noticeable moving point. Finding even a few earlier positions would tighten our orbit estimates and, with better stellar family maps, could narrow the range of likely birth environments. Finding such traces is a long shot, but long shots sometimes succeed, and the reward would be meaningful. More anchor points on the path this object has taken through the galaxy. The shift in our understanding from 7 bright stars to more than 3,000 stars in a 2,000 light-year structure requires a change in mindset. The original picture was not completely wrong. It was incomplete. The bright stars were always there, but they were only the tip of a much larger system. Seeing the full extent required better instruments, new analysis, and the willingness to question an old, comfortable view. Something similar may be happening with 3IATLAS. We see the bright coma, the jets, and the trajectory through our solar system. We now have Mars-based high-resolution images and improved spectra. We have reports of shell-like structures and unusual jet behavior. Each piece is real, but we may still be missing the larger context that makes them all fit together. As with the Pleiades before the more recent work, we might be focusing on the obvious parts while the deeper pattern remains hidden. The ongoing mapping of stellar families is changing our view of the galaxy from a random scatter of stars to a web of related groups and long dispersed associations. Somewhere in that web, in a system that may no longer look the way it did at birth, 3IATLAS was formed. It carries traces of that origin in its chemistry, its structure, and perhaps, if it is not purely natural, in any internal features it may have. Understanding those traces will require the same kind of effort that revealed the true size of the Pleiades, combining different kinds of data, asking new questions, and accepting that some answers may not fit neatly into older models. The Pleiades reminded us that familiar objects can hide much larger realities. 3IATLAS may extend that lesson, showing us what can travel between stars and what can endure across the immense spans of time and distance that define interstellar space. When stars destroy worlds, they remind us how fragile habitability really is. About 40 light-years from Earth, a small red dwarf star has shown why the search for living planets is more complicated than it first seemed. Astronomers have detected the first confirmed coronal mass ejection from a star other than our Sun, and it was powerful enough to strip the atmosphere from any planet unlucky enough to lie in its path. This is not a guess based on what we know about our own star. It is a direct observation of a blast of plasma racing outward at roughly 5.4 million miles per hour, dense and energetic enough to change the fate of nearby worlds. Researchers combined radio data with X-ray measurements to follow both the initial eruption and the shockwave as it moved through the star's outer atmosphere and into surrounding space. The crucial clue was a Type 2 radio burst, a pattern that occurs when a fast shock front passes through plasma and creates instabilities. That kind of signal is a clear marker of a coronal mass ejection and is hard to confuse with anything else. The star itself is quite different from the Sunday. It is a red dwarf, about half the Sun's mass, cooler and dimmer, but much more active. It spins around roughly 20 times faster than the Sun, and that rapid rotation drives a magnetic dynamo hundreds of times stronger. Its surface is covered in large star spots, places where intense magnetic fields rise up and distort the normal flow. When those fields twist too far, they snap and reconnect, releasing stored magnetic energy and throwing plasma into space. That process is what creates coronal mass ejections in the first place. Magnetic energy converted into motion and heat. We see similar events on the Sunday. Solar coronal mass ejections drive space weather at Earth, create auroras when they hit our magnetosphere, and, on rare occasions, disturb satellites and power systems. But the event seen on this red dwarf sits in the extreme upper range of what we know from our own star, in the fastest and densest fraction of 1%. If the Sun produced such an eruption, it would be considered a rare, severe outlier. For the red dwarf, this may be normal behavior. That point is important because red dwarfs are the most common stars in the Milky Way. They probably make up around 70% of all stars in our galaxy. Many of the exoplanets we call potentially habitable orbit such stars. The reason is partly observational. A small, dim star has its habitable zone close in, so planets that orbit quickly, cross in front of the star more often, block a larger fraction of its light during transits, and tug more strongly on it gravitationally. Our main detection methods are simply better at finding close-in planets around red dwarfs than Earth-like planets around Sun-like stars. However, having the right temperature for liquid water is only one part of habitability. A planet also needs to hold on to its atmosphere for billions of years. Repeated impacts from high-speed coronal mass ejections make that much harder. The observed event from this red dwarf traveled at around 2,400 kilometers per second. For a planet in a tight orbit, that means the shock and its particles can cross the star-planet distance in a matter of hours. There is no gradual buildup. The disturbance arrives quickly, compresses any magnetosphere, channels particles into the upper atmosphere, and heats that gas until it can escape into space. If such events happen again and again, over millions of years, the atmosphere can be stripped away completely, leaving a bare rock directly exposed to the stellar wind and high-energy radiation. Whether a planet survives, this depends partly on its own magnetic field. Earth's magnetic field, generated by motions in its liquid iron outer core, helps shield our atmosphere. Mars, which lost its global field early in its history, has seen much of its atmosphere eroded by the solar wind. The difference between a world with seas and air and a cold, dry rock can be traced to what happens deep inside the planet. Generating a strong magnetic field is not simple. The planet must be big enough to hold onto internal heat. It needs a liquid conducting layer that is convecting, and it needs to rotate fast enough for that convection to organize into a dynamo. Small planets cool and solidify more quickly. Close-in planets around red dwarfs often become tidally locked, always showing the same face to their star, which can change their rotation patterns and may weaken dynamo action. The set of conditions needed for magnetic protection is not guaranteed. These results have direct consequences for how we plan searches for life. New observatories, such as future space telescopes designed to study habitable worlds, will look for atmospheric signs that might hint at biology, oxygen, methane, and other gases in combinations that should not persist without constant replenishment. But if many planets around red dwarfs cannot keep their atmospheres in the first place because their stars are too violent, then the number of truly promising targets around those stars may be far smaller than the raw planet counts suggest. There are still possible paths to habitability. Life could exist underground or under ice, protected from the worst of the radiation. Oceans beneath thick shells of rock or ice might remain stable even if the surface is periodically sterilized. Some red dwarfs spin down as they age and become quieter, perhaps older. Slowly rotating red dwarfs pose less danger to their planets. Yet the simple habitability picture, find planets in the right temperature zone and count them, clearly misses much of the story. The space weather environment matters. The way this coronal mass ejection was detected also shows how much we gain from using several kinds of light at once. Radio telescopes, such as the low-frequency array, can pick up the Type II bursts from shocks. X-ray telescopes, like the European Space Agency's XMM Newton, can record the hot plasma directly. When both instruments see an event consistent with a coronal mass ejection, the interpretation becomes much more secure. This multi-wavelength approach can now be applied to many other red dwarfs, building up statistics on how often they launch extreme eruptions and how those rates depend on age, spin, and mass. We may even be able to identify which red dwarfs are comparatively safe and which are nearly certain to strip any close planet bare. All of this connects back to 3IATLAS by shifting our sense of what the galaxy is like. It is not a gentle environment. Space contains radiation, high-speed particles, blasts from stars, impacts from dust and rocks, and extreme cold. Life on Earth endures only within a narrow range of conditions, protected by our atmosphere, our magnetic field, and our distance from the Sunday. Remove any of these shields, and habitability collapses quickly. 3IATLAS has traveled through this harsh environment for an immense span of time. Between stars, space is close to empty and very cold. Cosmic rays pass through it constantly. Tiny grains of dust slam into anything in their path at high speeds. There is no steady source of heat, no thick atmosphere to spread out impacts, no easy refuge. Whatever 3IATLAS is, it has survived long enough to reach our solar system and still display complex behavior. Natural objects can be tough. Solid rock and metal can persist. Ice buried under insulating dust can last for billions of years in deep space. But maintaining fine internal structure, holding on to volatiles, or preserving any mechanisms that might activate near a star is much harder. Radiation slowly damages materials. Occasional heating and cooling cycles can cause cracking and fatigue. Over long times, a loose pile of rubble tends to break apart rather than stay in one coherent, responsive form. The red dwarf coronal mass ejection gives us a clearer idea of the stresses that planets and small bodies must handle. The same information, seen from another angle, is a guide to what any artificial object would need to endure to cross from one star system to another. It would need shielding against radiation and dust. It would need structures that can handle both deep space cold and intense heating near stars. It would need ways to store or generate energy over long periods, and enough strength to survive occasional strong forces without falling apart. Those requirements would leave traces. Heavy shielding changes an object's mass and thermal behavior. Systems for power and navigation might produce distinctive heat signatures or patterns of activity. Some of the puzzling traits of 3IATLAS, its thermal properties, its directed jets, its apparent structural stability under stress, look different if we allow ourselves, cautiously, to view them not only as natural processes, but also as possible responses to these engineering challenges. The violent event at the Red Dwarf does not answer the questions around 3IATLAS. It does, however, sharpen the background picture. It shows that stars can destroy as well as warm, that many habitable zones may in practice be hostile, and that survival in space, whether for planets, comets, or probes, demands real resilience. The images expected from Mars will sit against this wider context. They may show how 3IATLAS has weathered its long journey, or they may show an object that appears simple, while numbers and probabilities still point towards something far less easy to dismiss. When you start multiplying probabilities, when you stack one unlikely event on top of another, you quickly reach numbers that feel almost impossible. That is the region where 3IATLAS now sits. It is not just an odd object with one or two strange features. It is a case where multiple independent anomalies all point in the same uncomfortable direction. Each anomaly can be given an approximate probability based on what we know about comets, stellar dynamics, interstellar objects, and our observing history. Some might have odds of a few percent, others sit down in the range of tenths or hundredths of a percent. If those events are independent, the combined probability is the product of each individual probability. That is how compound likelihood works. You multiply, you do not add. Take just a few examples. The chance that a random interstellar object arrives on a retrograde trajectory aligned within a few degrees of the ecliptic plane is already low. Interstellar visitors are expected to come from all directions in three-dimensional space. The plane of our planets is special for us, but not for them. Add to that the precise timing and geometry needed for 3IATLAS to pass near several planets while staying hidden behind the Sun from Earth at perihelion. Each of those conditions alone is notable. Together, they form a very sharp constraint. Then add chemistry. An unusually high nickel content relative to iron runs against what we expect from standard nucleosynthesis and cosmic abundances. Add extreme negative polarization that does not match any known cometary dust, including past interstellar comets. Add low water content for an object that visually behaves like an active comet. Add a brightening curve and color near perihelion that do not follow standard thermal models. Add non-gravitational acceleration without visible fragmentation, jets that hold their orientation despite rotation, ghost shells and detached rings, and a gasless spectrum for a green jetting coma. If you assign each anomaly even a conservative small probability and then combine them, the total quickly falls to values so tiny they lose intuitive meaning. The exact number is less important than the trend. You move from unlikely but possible into a regime where saying it just happened no longer feels like a responsible explanation. The chance that all of this is pure coincidence under a simple, unusual natural comet model becomes effectively zero for practical reasoning, even if, strictly speaking, it is not mathematically zero. This is where Bayesian thinking becomes useful. Bayesian statistics is about updating beliefs in light of new evidence. You begin with prior probabilities, your initial sense of how likely each hypothesis is before you look at data. Then you ask, if this hypothesis were true, how likely is it that I would see this evidence? Comparing those likelihoods tells you how to adjust your beliefs. For 3IATLAS, the natural interstellar comet hypothesis starts with a high prior. Almost everything we see in space is natural. Interstellar probes if they exist, sit far outside our confirmed experience, so the artificial origin hypothesis starts with a very low prior. That is reasonable, but as the anomalies pile up, the weight of evidence shifts the posterior probabilities. The natural hypothesis can be kept only by accepting a long chain of rare coincidences. Each new anomaly forces you to stretch it further. The artificial hypothesis, in contrast, can explain several anomalies at once, with fewer separate assumptions. A targeted trajectory is expected if the object is guided. Low water content fits an object that is not a dirty snowball but something more solid. Unusual chemistry could reflect engineered materials rather than primordial dust. Persistent, oriented jets could be interpreted as thrust rather than passive outgassing. Structural integrity under apparently high mass loss and acceleration aligns with engineering requirements for a craft built to survive stress. Bayesian reasoning does not prove that 3IATLAS is artificial. What it does is compare how well each hypothesis accounts for the data with the fewest special excuses. When one model requires an increasingly elaborate set of unlikely conditions, while another can explain the same data more simply, the balance of plausibility starts to move, even if the starting prior for that second model was low. This connects to a broader question raised long ago by Enrico Fermi. If intelligent life is common, and some civilizations are very old, where is everybody? One possible answer is that we have not recognized what to look for. We have expected intentional signals, radio broadcasts, obvious structures, dramatic beacons, and have paid less attention to subtle, borderline cases. A cautious reconnaissance probe would not arrive with clear markings. It would be designed to look like ordinary debris. If a civilization wanted to observe without disrupting, it might send objects that mimic comets or asteroids, quietly sampling environments and moving on. Such probes would not broadcast loudly. They would not draw attention through obvious artificial signatures. The only hints of their nature would be small but persistent deviations from natural behavior, precise trajectories, unusual composition, jets that behave more like controlled exhaust than random outgassing, structural resilience under conditions that should break a fragile body apart. 3IATLAS, viewed through that lens, looks less like a random collection of anomalies and more like a signal encoded in physics itself. If humans were to design an interstellar probe intended to be detectable to a technology like ours without forcing recognition, we might choose something similar. Behavior that fits mostly within natural expectations but contains enough inconsistencies to invite deeper study. We might design it to be ambiguous, so that societies can debate and gradually adjust to the idea rather than being confronted with unmistakable proof. Ambiguity can be a feature rather than a flaw. Clear, undeniable evidence of extraterrestrial technology could have wide social and political consequences. Ambiguous evidence, on the other hand, allows different cultures to react at their own pace. Those ready to consider it can follow the trail. Those not ready can file it under strange but probably natural and move on. From an ethical standpoint, that looks like a careful approach to first contact. None of this shows that 3IATLAS is definitely an engineered object. What it shows is that, given the stack of improbable natural features, the artificial hypothesis is not irrational to consider. When natural explanations require compound improbabilities reaching beyond comfortable bounds, and when an artificial scenario explains several lines of data with fewer free parameters, Bayesian logic tells us that the relative weight of the artificial hypothesis increases. Critics are right to say that extraordinary claims need strong evidence. Saying that an interstellar visitor might be artificial is indeed an extraordinary claim. But the evidence here is not ordinary. We are dealing with a dozen documented anomalies, each independently surprising, all present in one object. At some point, a long string of unlikely but maybe events begins to look like something more. The most honest position at this stage is not to claim certainty. It is to admit that we do not yet know what 3IATLAS is, and that both natural and artificial possibilities should be kept open and tested. Natural origin should not be treated as the default simply because it is familiar. Artificial origin should not be dismissed simply because it is unprecedented. Both must stand under the same standard. How well do they match the data, and what do they predict for future observations? The upcoming high-resolution images from Mars will not directly answer probability questions. Cameras do not measure likelihoods. What they can do is add new facts. If they show clear natural features, a fractured surface with vent structures that match jet directions, erosion patterns that explain mass loss, textures that align with known materials that would strengthen natural models. If they reveal more unexpected geometry, smooth regions without obvious vent sources, or other unexplained patterns, the stack of anomalies grows. Whatever those images reveal, the statistical reality will still be there in the background. 12 independent oddities, each with low expected probability, all found together in a single interstellar visitor. That stack is the problem any final explanation must address. Explanations that depend on chances of 1 in a quintillion start to look less reasonable than explanations that ask us to rethink what might exist between the stars. At some point, adjusting assumptions may be more honest than insisting that a long chain of coincidences just happened. Tomorrow's images will not be neutral. The presentation will be carefully designed, the pictures processed and selected to support a particular narrative, and the spoken commentary will frame how most people understand what they are seeing. To make sense of it, it is as important to notice what is missing as it is to notice what appears on the screen. When the high-resolution camera on Mars takes data, it produces FITS files, flexible image transport system files, used across astronomy. Those files contain raw pixel values, calibration information, exposure times, and instrument details. They are not meant for public viewing. Converting FITS into appealing pictures requires choices about how to map brightness, how to stretch contrast, how to deal with noise, how to combine filters, and how to remove artifacts. Each choice affects which features stand out and which fade into the background. Logarithmic brightness scaling, for example, compresses the huge range between the glaring nucleus and faint outer structures. That makes it easier to see both in one frame, but it also hides real differences in intensity. A jet 10 times brighter than its surroundings and a jet 100 times brighter may end up looking similar. Smoothing reduces random noise, but also erases small structures that might carry important information. Unsharp masking sharpens edges and helps reveal boundaries, yet it can also create false outlines where none exist. Without access to the raw data and intermediate steps, it is difficult to tell where nature ends and processing begins. The camera's design also imposes limits. The images will be centered on the nucleus and inner coma because that is where the instrument was pointed and where the exposure settings were optimized. Faint, extended features, the ghost shells, detached rings, and distant jets reported from ground-based observations might lie outside the field of view, fall below the sensitivity threshold, or be washed out by the brightness of the core. Dynamic range is finite. If the exposure is tuned for the nucleus, the outer structures may vanish into noise. If it is tuned for faint halos, the center may saturate. Color will be another point of subtlety. High-resolution instruments often use a small set of filters, True color reconstruction requires multiple exposures through different bands, followed by careful calibration and combination. If only a couple of filters were used, or if they were not centered on the green wavelengths where the coma glows most strongly in ground-based images, the famous green color may not appear clearly or at all. Lack of visible green in those images would not, by itself, mean the green is gone. It could simply mean the instrument was not sampling the right light. Surface features, if they are resolved, will need careful interpretation. A dark depression could be a crater. It could also be a vent, a sinkhole, or a lighting effect. A bright patch might be exposed ice, or a region with a different texture, or just a slope facing the Sunday. The camera captures shapes and relative brightness, not composition. Turning those shapes into a story about geology or activity requires models and assumptions. Two teams starting from different models can look at the same picture and come to different conclusions. Even something as simple sounding as the size of the nucleus has built-in uncertainty. There is no sharp line where the solid body ends and the coma begins. Brightness falls off gradually. To estimate size, you must decide where to draw that boundary, how to subtract the coma's contribution, and how to correct for the point spread of the optics. Different choices yield different diameters. An object reported as 7 kilometers across might reasonably be somewhat smaller or larger once the error bars are included. The presentation will likely include computer simulations. Viewers may see animations of how a comet could produce the observed jets, tails, and brightening pattern. These models are not inherently misleading. They are useful tools for testing whether a given physical mechanism could, in principle, explain the data, but they are constrained by their starting assumptions. If the only mechanism allowed in the model is sublimation of ice, then every visual feature will be explained in terms of sublimation, even if other mechanisms, electromagnetic forces, internal outbursts, or active control systems might provide a better match but are not included. References to peer review, consensus, and the need for more data will probably appear. These are real parts of scientific practice. It is sensible to be cautious, yet appeals to more data can also serve as a way to delay confronting the idea that existing models might simply be inadequate. Individual anomalies may be addressed one by one with conventional explanations. The sunward jets reinterpreted as viewing geometry, nickel dominance as an odd parent body, low water as the result of long-term irradiation. Taken alone, each explanation might be acceptable. Taken together, they form a patchwork that depends on nearly every unlikely condition being true at once. That compound improbability will likely not be acknowledged. The structure of the press event itself carries information. Questions from reporters are usually screened and limited. Only some topics will be explored in depth. Others, such as the 40-day delay, the criteria NASA would consider as evidence of non-natural processes, or the full list of anomalies, may receive brief answers or be redirected toward general statements about ongoing analysis. The timing of this public release, before journal publication, reflects not only scientific urgency, but also political and public pressure. NASA must balance communication, reputation, funding realities, and scientific accuracy, and those goals do not always pull in the same direction. Language choices will matter. If the object is consistently called a comet without qualification, that labels it in the public mind before all evidence is weighed. More neutral terms like interstellar object or visitor leave the nature of the object open. How often speakers use one term versus another will reveal their starting assumptions. Emphasis will matter too. If jet geometry and size estimates receive long, detailed discussion, While spectral anomalies and mass loss issues are mentioned briefly, that asymmetry shows where attention is being directed. The composition of the panel will be another quiet signal. A group made up entirely of insiders with similar roles and viewpoints suggests a unified message, including independent researchers or those who have publicly raised questions, would indicate a willingness to entertain multiple interpretations. The way uncertainty is expressed will also be telling. Language like, "We think," "it appears," and "current models" suggest signals that interpretations are provisional. Statements delivered as if they were final facts about an object that is still under active study would be more about narrative than about science. The images themselves will almost certainly be impressive. Seeing an interstellar object at tens of kilometers per pixel is an extraordinary technical achievement, even if the surface looks unremarkable, pitted, rough, and similar to other cometary nuclei. That result would still have value. It would show how ancient interstellar travel shapes appearance and what kinds of structures survive. If, on the other hand, the surface shows geometric patterns, unexpected smoothness, or other features that do not match natural impact and erosion processes, those details will become part of the growing list of things that require explanation. It is important to remember that the first images shown will be a subset, chosen, cropped, and processed. The full dataset, multiple frames, different times, different viewing geometries will likely move through internal channels and formal archives before becoming widely available. Independent teams will need time to request, receive, and analyze those data. The initial framing, the story that reaches most people, will be shaped tomorrow in a controlled setting, so it is reasonable to expect professionalism, clear graphics, and explanations that sound plausible at first hearing. It is also reasonable to expect omissions, unanswered questions, and an absence of any serious discussion of the compound improbability problem. The key, for anyone watching, is to pay attention not only to what is shown and said, but also to what is left out, minimized, or deferred. Those absences are data too, pointing toward the boundaries between what is being presented for public comfort and what still lies unresolved in the background. The question that few people want to face is simple. If 3IATLAS were artificial, what would we reasonably expect to see? Many researchers avoid this because it feels speculative, but it is a legitimate scientific question. The only way to decide whether artificial origin is consistent with the data or to rule it out is to write down clear expectations and compare them with observations. Ignoring the question does not make it go away. Start with first principles. An interstellar probe has to survive the journey, operate in the target system, and do something useful when it arrives. That means protection against radiation, micrometeorite impacts, and extreme cold and heat. It needs power, either stored energy for long dormant periods plus active operations, or some way to generate power, such as radioisotope systems or solar collection near stars. It needs propulsion for course corrections and for shaping its path through a new system. It needs sensors, data handling, and a way to send information home or relay it onward. And if its builders are cautious, it also needs to blend in to look as natural as possible to young civilizations that might react badly to obvious signs of technology. A heavily shielded probe can explain several observations immediately. If you cover a vehicle in dust and ablative material, or if it sweeps up dust and ice over billions of years in interstellar space, the outer layer will look like old, reddened debris. Sunlight will heat that coating and produce a smooth, red continuum spectrum. Any underlying structure, metal, composite, or something more exotic would be hidden. Spectroscopy would only see the dust that is close to the featureless red spectrum we measure for 3IATLAS in key wavelength ranges. Low water content also makes engineering sense. Water is heavy. If you do not need large ice reserves, there is no reason to launch them between stars. A probe might carry a small amount of water as frost or as a minor component of protective layers, but most of its mass would be structural, shielding, and propellant chosen for performance, not for matching comet composition. Heated near a star, a little water might sublimate, yet it would not produce the strong water vapor signal expected from a typical comet. That matches 3IATLAS showing active jets and a bright coma, but only a few % water by mass in its gas. The odd nickel dominance with relatively little iron fits the same pattern. Nickel-rich alloys are common in demanding engineering applications because they resist heat and corrosion. If the probe's structure uses such alloys, erosion in interstellar space could release nickel-bearing dust into the coma. The resulting nickel-to-iron ratio would not match standard cosmic abundances because the material was chosen for function, not for following supernova yields. The jets become especially interesting if we think of them as propulsion rather than passive outgassing. Directional plumes, intermittent bursts, and maintained orientation despite rotation all match what we would expect from controlled thrust. A spacecraft with gimbaled nozzles or vectoring thrusters can keep its exhaust aimed in chosen directions even as the main body turns. It can fire in short burns separated by quiet periods. Energy for such jets would come from internal sources, not just from sunlight falling on ice. Under that interpretation, the energy budget problem largely disappears. Trajectory details also fall into place. A natural object arrives on whatever path gravitational encounters gave it. A probe is steered, passing close to Mars, Venus, and Jupiter, while remaining hidden behind the Sun from Earth at perihelion. Looks like deliberate geometry. Maximize observation of several planets, while minimizing the chance of detailed scrutiny from the one world with radio telescopes. The unlikely timing becomes expected if someone planned the path. Structural integrity under large non-gravitational accelerations fits engineering, too. Natural rubble piles often break up when forces become too strong. A probe designed for thrust would be built to withstand those loads, so that burning significant propellant in a short time does not tear it apart. The ghost shells and detached rings could be interpreted as exhaust shells from prior burns, expanding as nearly circular structures at speeds of hundreds of meters per second. The strong green glow without matching molecular lines might be plasma emission from ion or plasma propulsion, where ionized propellant produces color without the usual comet gas signatures. Taken together, many of the anomalies of 3IATLAS look less like a random collection of oddities and more like a checklist of features that an interstellar probe might have. Dust-coated shielding, engineered alloys, directional thrust, fine trajectory control, sturdy structure, and emissions that do not follow simple sublimation patterns. That does not prove artificial origin, but it shows that the artificial hypothesis is not just wild storytelling. It has explanatory power. The next step, if we treat this seriously, is prediction. If 3IATLAS were artificial, what should we expect to see next? Controlled systems tend to produce regularity. We might expect some jet activity to follow precise schedules, repeating with periods that are not simply tied to solar heating. We might look for small trajectory adjustments that occur at specific orbital phases rather than at random. We might search for changes in behavior when 3IATLAS is in positions where Earth cannot observe it well versus positions where we can. Signs of control might be subtle. If jets consistently avoid firing in directions that would push the object toward close Earth encounters, but do fire to favor flybys of other planets, that pattern would hint at planning. If activity switches on and off in ways that match simple algorithms, fixed intervals, or trigger distances from the sun, those patterns would differ from the smoother, temperature-driven behavior of natural sublimation. A well-designed probe, however, would likely work to keep definitive signatures hidden, if its purpose is reconnaissance without direct contact. Leaving no unambiguous trace might be part of the design. In that case, we should expect something like the situation we have now. Enough anomalies to raise questions, never enough to force a conclusion. Ambiguity becomes a feature, not a bug. It allows a developing civilization to notice and debate possibilities without being pushed into a sudden recognition. From that perspective, the discomfort many people feel about even asking the artificial question is part of the story. If humans were designing first contact protocols for visiting other stars, we would probably avoid dramatic displays. We would not arrive with giant ships hanging over major cities, and we would not stay perfectly invisible. The middle path would be evidence that can be found and interpreted by those ready to look for it. Behavior that natural models struggle to explain cleanly, but that can still be dismissed as strange but natural by anyone unwilling to change their view. None of this tells us definitively that 3IATLAS is a probe. The careful stance is not to declare that we have found alien technology, nor to insist that such a thing is impossible. The right attitude is to admit that artificial origin is a hypothesis that can be framed, given expectations, and compared to data alongside natural hypotheses. We can use the same tools, statistical reasoning, predictive checks, and future observations to weigh it. Avoiding this line of thought because it feels risky or bad for careers is not science. It is social pressure. Scientific practice asks the questions that follow from the data, even when those questions make us uneasy. It lays out competing hypotheses, tests them as far as the evidence allows, and is willing to revise conclusions when one model consistently fits better than another. The images from Mars will not settle the matter. They may show vents and fractures that strongly support natural models, or they may add yet another layer of strangeness. Either way, they are more data points to feed into the comparison. What matters most is whether we allow ourselves to ask, in a clear and structured way, what 3IATLAS would look like if it were artificial, and then compare that picture with reality. 3IATLAS has given us facts that do not fit comfortably inside our old expectations. 12 major anomalies, extremely low combined probability under simple natural assumptions, and behavior that lines up surprisingly well with what we might design into an interstellar craft. That is not proof, but it is enough reason to treat the artificial hypothesis as one option on the table, to examine it with the same seriousness that we applied to every other explanation, and to accept that the universe may contain possibilities we did not plan for. In the end, how we respond to this case says something about us. We can choose to treat 3IATLAS as a test of our willingness to follow evidence beyond comfort, or we can choose to fold every anomaly back into familiar stories, no matter how strained they become. Tomorrow's presentation will show us images, our reaction to them, what questions we ask, which explanations we accept, and how open we remain to revising our views. Will show us something else, whether we are ready to let data, rather than habit, guide our understanding of what might be passing through the dark between the stars.